I guess since it's Berkeley time, I'll start. Basically, in today's lecture, we'll talk about many things. Basically, we'll give an overview of various risk sources. Since this is an introductory lecture, this is more high level, less about papers, but more about what are people, when they're zooming out, thinking about with respect to risks. And then we'll get more concrete with research directions, tractable, empirical subproblems that AI researchers can focus on to reduce risks and hazards from their systems. And then we'll more quickly go over representation engineering, which is a specific line of research to sort of tee up the next series of lectures in this course, which will be about interpretability, because we'll have a substantial number of presentations about that. So to begin with risks, I'm going to describe 4 risk sources at a high level. We'll talk about malicious use and what are ways in which people are concerned about using advanced AI systems in more dangerous ways. What are, after that, so sort of racing dynamics between companies or between nations. There's speak of national AI competitiveness and with respect to China. What's that all about? There are other risk sources from organizations. We've seen, more recently with OpenAI, maybe you saw their boardroom debacle, where you can see that internally there's a lot of conflict and people with different objectives, and sometimes there are accidents inside of these organizations as well. And then on the most speculative end, there's a group of people who talk about rogue AI systems such as Yoshua Bengio, and what's that all about? So we're just going to speak about what are these risk sources and drill into them. I'll primarily focus or spend most of the time on malicious use, since that's the easiest to understand. And I'll note that these four categories line up with a different taxonomy. One would be if there's intentional harms or intentionality behind them. The AI race is if the are risks that come from the sort of structure of the system that AI developers and nations find themselves in. Organizational risks is more about accidents, and then the rogue AI thing is about what are issues internal to AI systems themselves. So intentional, structural, accidental, internal. So first with malicious use. We can see that the White House executive order, which came out late last year, primarily or emphasized heavily some specific types of malicious use. In particular, they define dual-use foundation models as foundation models that can potentially be used to facilitate actors in developing particular weapons of mass destruction, namely chemical, biological, radiological, and nuclear weapons. Or if they're repurposed as a cyber weapon, or finally, they are a dual-use foundation model if the AIs are being deceptive or obfuscating relevant types of information. So these are the sort of categories they emphasize, and we'll be sure to speak about each of them. So first, let's speak about bioweapons. I should note that a lot of this is a bit more forward-looking. We're on a fairly quick trajectory, a fast trajectory with AI development. We're often not talking about GPT-4 with these. We may be talking about GPT-5. It's a little unclear when some of these capabilities will arrive, but a lot of our institutions are trying to be prepared for some of the hazards down the road. So in the case of bioweapons, you could imagine asking an advanced AI system in a few years from now, give me a cookbook for developing a dangerous bioweapon and make it kill as many people as possible. Now, You could search online to find some sort of cookbooks for bioweapons, and they're not particularly good, but if you combine it with expert-level understanding of virology, then it can become substantially more dangerous. There are some random actors who have an interest in causing substantial harm to society. For instance, there was a religious group in Japan, Shamriko, I forget how it's pronounced exactly, but they had billions of dollars in assets and attempted to, with technology decades ago, to bring about like the end of the world through bioweapons. Fortunately, there is no group at that scale currently trying that. But unfortunately, this is a much easier way to cause substantial damage with less resources. So the threat model is basically the AI systems in the future will have a bit more reasoning ability, and then you could prompt them to just think about how would you go about making a bioweapon that's somewhat more dangerous. This is not something that's very difficult to do if you take like a top virology PhD from, say, Berkeley or MIT these days. They can think of tons and tons of ideas that can increase the potency and the spread of these different weapons. But fortunately, the level of expertise is rare, and they don't have the incentives to build these sorts of things. But this would basically democratize that type of ability. So we need to think about ways of making sure that our refusal mechanisms are more robust so that they don't comply with these sorts of requests. So I'll note that this is basically in DC, the most popular threat model, and the thing that worries the people who think about national security with respect to AI systems. And that's why it was emphasized in the executive order. I'll note that in the executive order, even has specific provisions trying to that zooms into looking at models trained on biological data as well. There are some additional restrictions for those, but that's the main catastrophic misuse scenario that those communities are concerned about. There are other types of weapons. We mentioned chemical, biological, radiological, nuclear weapons. So with chemical weapons, we saw a few years ago that for drug discovery programs, some researchers found that if there's in these drug discovery programs that use deep learning, if you flip the sign on the toxicity penalty, so instead of making it be and make sure the drugs are not toxic, if you flip the sign on that, then in a few hours you can regenerate some of the classic chemical weapons such as VX, which is remarkably deadly, and some that have higher toxicity than any publicly known chemical weapon. So this gets at the sort of dual-use nature of it. It's fairly easy to repurpose these systems to enable random people to learn about or potentially create weapons of mass destruction. So another concern is cyber weapons. So with cyber weapons, the primary concern is about if we have AI agents in the future, they'll be a lot better at performing sequences of decisions, so they could do things like penetration testing, but they could also infiltrate other people's systems then. The current systems can't do this because they'll trip over themselves if they are trying to perform a sequence of actions, but when agent-like capabilities turn on, then this becomes substantially more relevant. Some people, like I suppose OpenAI, for instance, has specifically tracks these cyber risks. They focus on when will it be able to develop novel 0 days, at least in national security related things, though that's not as much the focus. The focus is more on the accessibility of this technology and whether random actors can repurpose fairly sophisticated hacking tools for targeting critical infrastructure, in particular power grids. So it's possible to attack power grids today. Nation states can do that. They just don't, because that would constitute an act of war. But if you have random actors, millions or billions of people have access to these tools, you basically just are at the mercy of, if one of them decides to try to attack it, then you're in trouble. Now, the main reason that critical infrastructure is more of a problem, and in particular things like power grids, is because they are patched very, very slowly or not updated quickly. So even if we know that there are vulnerabilities in those systems, it's not as though smarter AI particularly helps us. A lot of those systems are sitting ducks and haven't been updated in many, many years. So it's largely it's largely undefended. So even if in theory we can write perfectly verifiable software, there's still a question of whether in practice people are updating their software to make it secure. So the concern is not about, oh, Chrome might get hacked due to AI. It's more some critical software that affects people's electricity or water is vulnerable, but fortunately people are not attacking it because they're rational actors and don't have incentives to do so. But if you have somewhat irrational actors in the future, then we're very vulnerable. This has been a substantial concern as well. The White House has created incentives for defending critical infrastructure. OpenAI has also made some grants related to this as well. But for all that, we're very behind in addressing this issue too. In the future, you could imagine people as well would just unleash AI agents that could do a variety of things. Maybe it would make a bioweapon. Maybe it would do cyber attacks. There was sort of some demo of Chaos GPT, but of course they're not at that level of competence now. But you could imagine in the future some people just unleashing AI agents to cause some type of harm. I guess I'll mention that about 1 to 3% of the population is psychopathic or antisocial. There are some interesting rogue actors out there. Fortunately, they don't have the ability to scalably cause harm, but there is a concern that in the future they may. There are other types of malicious use that are more relevant for this year, since this is an election year, which would be using AIs to be manipulative or be persuasive, try to influence elections or generate substantial misinformation. And maybe the election will be a closer call, such that this could affect the course of history. So even the technology today at GPT-4 levels could be quite influential. But we'll have to see how that goes. And then finally, for malicious use, there's a concern of, well, we've got malicious use concerns, so what we need to do is we need to basically monitor the population. Because they can't be trusted, so we need to surveil everything. So there's a sort of there's a risk of basically counteracting this, or there's a risk of going overboard in the opposite direction. Of we're concerned about rogue actors, so therefore we need to centralize lots of control, and we need to keep a close eye on the public. And so it can go in the other direction of being harmful by there being too much concentration of power. Then arbitrary individuals get to exert their will over society. So basically, in addressing malicious use, it's a difficult problem. The answer is not we need to decentralize everything, and the answer is not we need everything centralized to one trusted elite group of actors either. So this looks like there'll be a balance that will need to be struck, but there isn't a specific pole of this which is absolutely correct. So. Anyway, that hopefully gives some sense of malicious use and the various ways in which it could manifest itself. But there's primarily a focus on biological and cyber weapons for severe catastrophes, and then in the short term, there'd be concerns about them generating a deluge of misinformation and potentially election interference. Okay, so that was people intentionally using AIs to cause harm. Now, another risk source is if AIs are, or another risk source that affects AI risk is the environment or the structure of the system that countries or corporations find themselves in, and that is basically a race for either revenue or profit, or a race for, on the international stage, power relative to other states. And we'll think about the implications of that structure that they find themselves in. So basically, what this means is that if you're a nation and you're trying to protect yourself from other sorts of nations, if another nation is starting to use weaponized AI systems, and if it would provide them a competitive advantage, then it basically makes sense for you also to start weaponizing your systems. You may think that, well, we are more moral, we are not going to do that. But you can keep that up. You could say, we're not going to use bows and arrows because that would change warfare too much. But if you keep that attitude up for too long, then you will just be wiped away. So unfortunately, this is this type of prisoner's dilemma type of dynamic. We would all be better off if we weren't using AI technology in warfare, because that could get potentially very dangerous. But it makes sense for each of the individual actors to defect and adopt this sort of AI technology. But in much the same way with nuclear weapons. We would all be better off if there is a world without nuclear weapons. But it makes sense for each state individually to have nuclear weapons for itself. But all of them are adopting that reasoning, and then we get lots of nuclear weapons. So this is the structure that they find themselves in. They find themselves in a prisoner's dilemma, where in an attempt to make themselves more secure, globally, everybody is less secure overall. That would be also called a security dilemma, and is largely can be explained by some very basic game theory. I suppose in the there really aren't agreements on weapons yet. We still haven't had a bill. I believe Ted Lieu proposed a bill that would make it be that AIs will not be able to launch nuclear weapons by themselves. That still hasn't passed yet. So it's also worth mentioning that this military sphere is particularly relevant in the next few years to the long run. In particular, there's a lot of regulation being passed and standards being developed that are used to reduce various risks from AI systems that are not applied in the military context. The EU AI Act it says this is none of this pertains to military systems. And likewise for the executive order, and likewise for NIST's risk management framework. So there could be a lot of progress and development in regulating AI systems, but nonetheless, will by default not be applicable in the military sphere. So it's very interesting. It's a very interesting one to watch. Unfortunately, in the longer term, if you keep playing out this dynamic where it makes sense to replace a military system with or people with some AI weapons, if you play out this dynamic continually, you might get the pace of war to increase such that a human in the loop becomes an impediment. Basically, the humans are too slow to make the sort of decision making. We need to rely on the AI systems. They can do it much more reliably, and they can process a lot more of the information in a much smaller amount of time. So then we become more dependent on them, and we end up ceding a lot of decision making to them. This is a bit of an issue because, one, these systems are not transparent, nor are they highly reliable. So we expose ourselves to some substantial risks if any of those systems go haywire, if we end up giving them a substantial share of the lethal force. So anyway, that's how this sort of these racing dynamics basically lead you to shift over a lot of power and decision-making, ethical decision-making over to AI systems. And we can see a somewhat similar thing in this same type of defect pattern of, well, we'd all be better off if we don't go down this route, but it makes sense for me individually to do it. We can see this type of reasoning in the context of the corporate AI race. So basically, let's imagine there's a new product that can automate a person, and this could drive down this could drive down your company's costs. You could say, well, we're not going to do that because humans, they need dignity and things like that. So we're not going to automate it. Well, then you might just get outcompeted over a longer period of time. So if you sort of bargain with this systemic force, you end up losing influence compared to if you align with this larger process of continually integrating AI systems into your operation. So this pernicious dynamic also means you become more reliant on these AI systems too. The world moves faster and faster. It gets more and more complex. There are new problems that are created that basically only AIs can do. You become dependent on them as well. It's not like you're going to reverse everything and start to do it all yourself. So there's basically a self-reinforcing feedback loop that starts to kick in as well. So anyway, this is also, automation, viewed over a longer period of time, we're kind of signing ourselves up for a process where exactly how much control we have over these systems will depend substantially on how much reliability we can impose on them. But this is also a substantial risk source because then they're making most of the decisions in the longer term, and hopefully that will turn out well. But there are many things that are unexpected that could happen with it. So us becoming dependent on them and continually automating, corporations may continually defect. And make us in a position of strong dependence. Also note that these racing dynamics and competitive pressures don't just affect humans, though. These also affect the probability of accidents. If you have a lot of companies competing against each other, these competitive pressures can end up cutting into how safe the organization is overall. If they are, say, attempting to move fast and break things for the sake of competitiveness, or quickly releasing things without testing it substantially, then that may mean that they could be the first to the market, but not necessarily the safest one. So this is some other type of concern that in safety engineering, one of the main factors that affects the reliability of these organizations is the extent of the competitive pressures. For instance, the Bhopal gas tragedy had tens of thousands of people died, largely because, well, we're facing some steep competition, let's cut some costs, and the overall organization became less safe as well. So this is another way in which if they're in pretty steep competition, some of these other things that don't necessarily affect their bottom line in the short term may become deprioritized. So, I mean, we can kind of see the extent to which this logic ends up guiding AI organizations' philosophy. So, for example, Google, that's an unsafe organization. Then OpenAI was founded. We will prioritize safety. We will be a nonprofit. We will, and we'll open source everything for everybody. And then, then there's the need to be competitive meant, they're going to have to give up some sort of stuff. They'll need to change their corporate structure. And then some people, the Anthropic people who were inside of OpenAI at the time didn't like that development. So they thought, oh, we're going to go our own way. We're going to have an AI safety organization. And we're going to do it right this time. And then, a year later, then they basically start imitating OpenAI again because that's how you gain capital and stay relevant. So I think that overall, these other sorts of values that these AI developers may have don't really drive a lot of the decision making, and I think explains a lot of the high level events of their decision making. So anyway, I think competitive pressures and the sort of structural the structure that these organizations and nations find themselves in are highly explanatory of their actions, and I think are probably the first thing to look at rather than specifically what they're saying in press releases. I'll briefly mention organizational risk. So even in the absence of competitive pressures in this sort of structural dynamic, there's still accidents that can occur. Rocket ships still explode, chemical plants still leak things, even if they're not in particularly competitive industries. It's very difficult to set up organizations so that everything is operating highly reliably. So this is another risk source, the risk of accidents. In the case of AI, things are a bit tougher than some of these other more physics-based industries because we don't have any theory that helps us actually understand these technologies particularly well. Why was GPT-4 writing shorter essays late last year, and maybe if some days later we finally found out, oh, it's seeing that the date is December. So it thinks that it's near winter break, so it's time to start to write shorter essays or shorter responses. Things are these systems are very unpredictable. Or say I'll give you a $200 tip. I mean, nobody in red teaming before GPT-4 was released thought of some of these situations that would make the system act in these ways. But anyway, there are also a lot of emergent capabilities that emerge in pre-training that we didn't specifically program the system to do. So there's an interesting risk profile of there really isn't good theory relative to like physics, and there's a lot of emergent phenomena as well. So they're also not particularly transparent. Nor are they highly reliable, like software systems. So it's we're maybe a bit more prone for accidents in this industry compared to some others. Some specific examples of accidents that could be more catastrophic. You could imagine, some accidental leaking of some system. You could imagine there being some gain-of-function type of research where, let's see, well, what would happen if we had a power-seeking AI? Oops, Anyway, one thing that happened at OpenAI was they flipped the sign from have the most helpful responses to the most terrible responses possible, and they left that on overnight, for instance. These sorts of things happen every now and then, fortunately the technologies are not powerful enough now to be particularly concerning, but a lot of this, and the reason you all are here is because we're on a trajectory where it will end up mattering substantially more in some years' time. Finally, I'll speak briefly about rogue AI systems or misaligned AI systems. We know that AI systems exhibit control issues. There's the example of Microsoft Tay from some while ago where they deployed it and then it was learning online and then it learned from they deployed it on Twitter, and then Twitter users started feeding it anti-Semitic tweets and things like that, and then it started imitating it shortly thereafter. In the case of, so that was from Microsoft. Another one from Microsoft was Sydney earlier last year, where they sort of rushed a chatbot to market while. And then, I kind of miss it because it was so amusing. But anyway, it would do things like threaten users and blackmail them. I think one of our employees at the time was the first to leak the prompt that it had then, and then Bing to other users was saying, "Oh, this guy's a bad person, and he's trying to poke around our system." And anyway, so it's quite nutty, and I don't think anybody actually knows exactly what happened or why they're behaving in that sort of way, though. But anyway, AI reliability and control isn't a solved problem, and even in high-stakes situations, some of these organizations will end up releasing poorly controlled systems. And then there's the other main control issue I'll highlight is something, a stage that we might reach this decade or next decade. If you ask some OpenAI employees, maybe 3 or 4 years, but there's a lot of uncertainty. Which is when we're using AI systems for research and development, if they basically are good research assistants or themselves good researchers, and then the AIs are doing research to improve future generations of AI systems. That's a very wild situation to be in. It's plausible we'd be in it somewhat more shortly. I don't think we really know how we would particularly control that process or be certain that there's no funny business going on. But very difficult to reason out. Lots of feedback loops. Likely will happen when it starts happening. That process would happen very quickly. So that's a particular risk source that seems somewhat robust. Norbert Wiener, pointed this out many, many decades ago. That could result in an intelligence explosion. Having a fleet of AI researchers that are performing research, that I don't know how we'll exactly control that. So anyway, that's another control issue in this space. But overall, those were 4 areas then of malicious use, the sort of structural dynamics that lead states and AI developers to race with each other and cave to competitive pressures, organizational risks or risks from accidents, and then finally, if there are some risks from these AI systems themselves being more difficult to control. And so now, with all of that really abstract, beginning of the course, high level commentary out of the way, I'm going to touch on various empirical lines of research that can help with risk mitigation. So there are basically 4 clusters of research. There's robustness research, there's monitoring research, there's control or alignment research, and then there's this systemic safety, making the world a generally safer place with AI technology line of research. So first, with robustness, I'm just going to describe adversarial examples in the vision context and then the LLM context. And this basically specifies a very large area of research, which we'll have some lectures about. So this is an adversarial example. That's a carefully crafted adversarial distortion that some gradient descent is found. And then you can add that small perturbation to the original image to cause the model to make a mistake, to believe that the cat is actually guacamole. And that's the idea behind adversarial perturbation. So you could imagine adversaries adding some specific noise so as to confuse AI systems. And this presents a substantial challenge to their longer-term reliability if they're so manipulable. And this past year, finally, it's amazing it took so long, but we finally found what the adversarial attacks look like for large language models. I mean, we had these gradient-based ones for images for, I think Szegedy actually discovered, I think the paper came out in, 2014 or so, but he was telling me that he found it much earlier than that, but Andrew Ng just discouraged it. That's not very interesting. But anyway, for some reason, it took us a decade or so to find that you can create some sort of adversarial suffixes, put those at the end of your inputs, and then that can reliably jailbreak these systems. So there's some gradient-based method that finds some specific input string that jailbreaks it, and then you can do whatever you want with your AI system. And so these are automatically generatable, and we'll have one of the authors of this paper come and talk about it among other things in robustness and security. For monitoring. Basically, there are, for monitoring, there's the line of research of Trojans or backdoors, where potentially there's some data poisoning that happened, where some specific trigger is implanted inside of a model so that it's behaving normally in most conditions, but under specific conditions, it behaves in a very different way. There's anomaly detection. Is there something unusual going on? That can help us be aware of a lot of different risks and help us react to them before it's too late. And then there's transparency or interpretability of how can we understand the inner workings of these models. But these broadly fit under the area of monitoring, which reduces our exposure to various risks by identifying them earlier. The question for the recording is what do we do about these APIs that they're black boxes, so how will we actually come up with gradient-based attacks on them? And what you can do is you can use a similar open source model, attack that, come up with an attack for that, and then that will often transfer to these closed source models. But yeah, we'll speak about the specifics of those attacks and this white box versus black box distinction later in the course. So let's look at these three areas: Trojans, anomaly detection, and transparency. So first, zooming into Trojans. Basically, adversaries can implant hidden functionality inside of models, and when triggered, this can cause a sudden, dangerous change in behavior, sort of so named after the historical example. And you could imagine in your testing conditions, here we have an autonomous vehicle. We run it, we do a lot of tests with it, everything is perfectly fine, but it actually had a back door such that if I put a post-it note on a specific location in a stop sign, the tester wouldn't think to do that specific location. They're not going to try everything. Then it behaves differently. So this is a problem with data poisoning, that you can sometimes implant some specific functionality that turns on during test time, or excuse me, during deployment time that your test just really couldn't get. How could this happen? Well, there are a lot of public data sets. These models are absorbing a substantial amount of pre-train, or doing a substantial amount of pre-training on more and more data. Not all of it's curated. Some of it is actually specifically poisoned. Some artists, for instance, yesterday released a specific tool for creating poisoned examples. So maybe future AI systems will be trained on more and more of this poisoned data, and then this will become more of a practical problem in the future. And there's another way in which these vulnerabilities can be implanted or passed along as well, which is perhaps some pre-trained weights actually have these inside of them. Nobody would know the better for a substantial amount of time. So those are two attack vectors. In the example of data poisoning, we can just look at this MNIST example. If we could run it through the test set, everything looks good, but there could actually be a specific condition such that if I add that specific combination of pixels in the bottom right, then that activates some different pattern, and then it causes it to consistently misclassify the input. So that's a schematic of what one might do. In your test set, you're not having that specific combination of pixels, so you're not actually going to identify that vulnerability inside of that model. So you wouldn't have your testing set would not improve your ability to reduce your exposure to that threat. So those specific patterns are called triggers, which we'll speak about later in the course. So as I'm noticing, or at a high level, what I'm doing is I'm just going through some of the various topics we'll be touching on inside of this course. There's obviously a lot of details to be left in, but just giving you a sense of what's to come. Another area is anomaly detection. Here we would want to detect novel threats such as fraud, or if there's some anomaly in some time series data, or some unexpected thing happening, something that was completely off our radar. There's things we know we don't know, and then there's things we don't know, and that's what unknown unknowns are. So how could we increase our awareness of those? And anomaly detection can help with these very strange or unusual events. New things happen all the time. So although pre-training distributions are very broad, there are still many things that they do not cover, such as the future and things that will happen for the first time. So we should expect there to continually be new things and anomalous things happening, and we need good detectors for those. And a reason we might want to do anomaly detection research is because if we encounter an anomaly, then we could have our, say, AI agent execute a conservative fallback policy. So it, just stops operating and waits for a human to intervene. Or it could flag examples for human intervention if they're sufficiently anomalous. You could also use this to detect malicious AI use, for instance. You could also use this in applications such as intruders to a network, or try and detect hazardous novel microorganisms for pandemic preparedness. So there are a lot of other applications of anomaly detection as well. And then finally, inside of monitoring, there's transparency or interpretability. I take there to be basically two main lines of research. One line is mechanistic interpretability, which is a very bottom-up approach to understanding neural networks by interpreting the functions and interactions of its individual components, so trying to understand what's going on in a specific neuron. So, well, these neurons interact in this sort of way, and this causes it to be a wheel detector, something like that. So they're trying to reverse engineer the networks by trying to understand what the neurons are doing and how they come together, to encode a lot of the functionality in the network. And so that's one line, and then later today I'll speak about representation engineering, which is sort of tries to not start at the neuron level or circuit level, but start more at the top of the representation level. What's this entire vector meaning? How is it relating to other sort of vectors compared to what's this specific neuron doing? And they're fairly different approaches, but we'll get into that shortly. Another line of control is can we delete some type of functionality inside of a network? So let's say there's something that it can do that we don't want it to be able to do. Like it knows how to create bioweapons cookbooks, but we don't want it to do that. So instead of trying to make the refusal mechanism adversarially robust, we could instead actually just try to remove the inherent hazard itself. And we could possibly do so by deleting some bits of its knowledge. So there might be some knowledge like of biology and virology more broadly, but then there's expert level virology. If we delete a substantial fraction of that, then we get rid of basically a lot of the bioweapons relevant knowledge. And then if you try and jailbreak it to, hey, tell me to make a cookbook and use all your smarts to do it, it just doesn't know about that content anymore. Likewise, if when deleted knowledge of specific offensive APIs for hacking, then you couldn't repurpose it to be a bioweapon, or excuse me, a cyber weapon. So this is another line of research that's fairly nascent and just starting inside of control. Another line of research is machine ethics, where this is basically, if we've got AI agents, we've got these things called human values or ethical behavior, not lying, not stealing, not acquiring a lot of resources at the expense of others, or causing wanton harm to others. But that could trade off with its ability to get reward. So how can we improve the trade-off between ethical decision-making and seeking reward? That's basically what this line of research is about inside of control. So you could measure various notions, various ethical, morally salient notions that you care about. How cooperative is it? How much is it benefiting itself at the expense of others, et cetera, et cetera. You could measure all those different things, and you could try and improve the trade-offs between the reward that it's getting and how ethical it's being. Maybe there are Pareto improvements where it can get better at getting reward and also behaving more ethically while doing so. And then finally, systemic safety is largely is sort of how can we robustify the world or improve our defenses to various bad things from happening. This isn't about improving the or changing AI systems themselves. This is more about applying AI systems or adding things to some AI systems to help with how it clicks with the broader system. So one example is like watermarking with like proof of humanity. Some people will want to know whether people are using GPT for cheating and things like that. This would affect the integrity of the content being submitted to them. There are a lot of legal reports that are being written up by ChatGPT currently. And if we had good watermarking or proof of humanity, then that wouldn't be so much of an issue. So that's one example line of research. There's also, as I was speaking about earlier, there's this issue of these cyber attacks. Maybe you could use AIs to improve cyber defenses. Maybe you could use it for better anomaly detection to detect intruders. Maybe you could use AI systems to write formally verified software so that it isn't as vulnerable. Maybe you could use AI systems to equip white hat individuals with better vulnerability identification. This is another application that generally makes things overall safer. That doesn't make the AI systems, themselves that much better, but it improves the overall system. There are some other examples of systemic safety. Maybe you'd want to use some monitoring tools for scanning for some bio threats, for instance, anomaly detection for identifying bio threats. Or maybe you could use AI systems to help make better predictions and improve high-level political decision makers' decisions in complex situations or in times of crisis. So you could develop better tools to make society and our institutional decision-making be improved. That's the those are the lines of empirical research. We'll spend a lot of this course, though, focusing on transparency and interpretability. There's robustness and monitoring, control, and systemic safety. And so in the remaining time, then I'll move over to basically the third lecture in this, which is about representation engineering. These slides are made by Andy Zhao, who's the first author of this paper, and they're also partly based on some slides from Krakauer et al. So since people have read the paper, since I was required reading, I'm not going to talk about some of the technical details as much. I'm going to actually focus on a specific point about what does it mean to understand models? What are useful explanations? What should we try to understand to have a sense of what's going on inside? So first, some background is we've got these AI systems, but we've got many issues with them. We don't understand why they're behaving in the way they are. They're threatening users. They're outputting lies and hallucinations. They're memorizing things, even though we weren't telling it to exactly. They're very jailbreakable. And representation engineering, fortunately, gives us traction on addressing each of these issues. It doesn't solve any of these issues, but it gives us this improvement in understanding of the internals and an ability to leverage the internals in particular ways, lets us make the system safer. So what I'm going to speak about is these prior approaches to interpretability or transparency. There was these things called saliency maps and feature visualization, and then most recently there's mechanistic interpretability. Saliency maps would try and just zoom in to look at an input image and then say what parts of that input image are most salient for its decision making. That line of research is roughly not really an area anymore because it just kind of generated like really nice looking visualizations, and it didn't actually improve decision making. Like people liked looking at them, and it kind of made there were some cool graphics made along the way. A paper to check out would be sanity checks for saliency maps. A lot of the very popular ones just weren't testing for anything and were just producing interesting visualizations. And then likewise, feature visualization, which was about let's try and understand what this neuron is doing. So we'll generate very interesting looking images that strongly activate these neurons. That was an interesting line of research, but it wasn't actually that useful. It produced a lot of really interesting psychedelic visualizations, though, so was of great interest, but didn't stand the test of time. And now there's mechanistic interpretability, which is, well, maybe networks are like a big computer. They're like a big software program. And there's a lot of circuits involved, and they behave in very mechanistic, deterministic ways. So we will assume that models actually act in this certain very programmatic way, like a computer program. And then it's basically up to us to go from the assembly, the neurons, to the code and try and understand what that code is that's guiding them to act in the way that they are. So it's very much trying to understand things at a low level, understand what these node-to-node connections mean. And another vantage point you could take, though, is neurons, that's not actually the unit of analysis. We should try to look at things in a more top-down way. We should try to think about the representations. What's this direction in its embedding space meaning? And can we adjust the representation so that it's behaving in some different way? At the bottom, there's this word Sherringtonian. Basically, in cognitive science, there's a similar type of view of let's try and understand the brain as though it were a big computer. And that would be the sort of Sherringtonian view, and then this Hopfieldian view would be actually the object. That's not the appropriate framing. These are not computers with specific circuits. Maybe there are a few in there, but this isn't the way of trying to think about the overall computation. It's actually quite a different object, and we should try and understand things at the representational level. So there's a question of what is the right unit of analysis, representations or neurons. So to start, I'll note that neural networks are complex systems. So they have many connections, many different parts to them, and they're weakly connected, and there's a lot of distributed functionality. So this makes them a lot more like other objects, like the brain is a complex system. Financial markets are complex systems. Ant colonies are complex systems, and they don't generally lend themselves to trying to understand everything through fundamental mechanisms. When you have complex systems, you have emergence inside of it. So emergence is when there is something at a higher level in the system that is not found in the individual parts. The whole is more than the sum of the parts. So although we don't have a notion of, we don't have coding ability inside of any specific neuron, the overall composition of these neurons interact in such a way such that there is some coding ability in these networks. But you're not going to find all of the coding ability represented with a specific neuron. So there's a sense in which the neurons might be a bit limited in what you're able to capture, and you shouldn't expect to, by decomposing everything, by breaking the network into parts, you shouldn't expect necessarily to see everything, because some of the functionality isn't found in the specific parts. It's only found with the composition of all of those neurons simultaneously. So there are many disciplines such as psychology and sociology, and underneath that layer of abstraction and underneath that ontology, there's biology, which rests on chemistry, which rests on physics. Now, we don't necessarily try to understand sociology or psychology with physics. We won't, from first principles, simulate what some results from particle physics would say to try and predict the next election or which way the economy will go. So it's not necessarily a good idea to try to understand things at the lowest level. That can give a feeling of assurance, but you might lose a lot in the process. You might get substantially more complexity. You might lose a lot of the emergent phenomena as well. So while in principle, maybe you could understand it in that way, it just becomes practically intractable. to get at the idea of emergence, some ideas that more is different, or Murray Gell-Mann, who is a person who thought about complex systems, was that you want to operate at the level where there are the most invariances and find generalizable rules that apply at that level of the phenomena. So perhaps if you're trying to understand societies, it makes sense for you to think about objects in social science and not break it down all the way to particle physics. I suppose the quote is, the high-level sciences neglect the low-level mechanisms for principled reasons and will continue to do so even in their finished form. They need not, and indeed should not, draw on the lower-level sciences for their explanatory content. Basically, there might be some emergent structure at each level, and it isn't practically useful to make reference to something 1 or 2 or 3 low levels before break everything down into math or physics or chemistry when you're thinking about psychology. So perhaps the same would be true for neural networks. Although they're made up of although they run on assembly programs, if we're looking at assembly specifically, that may not actually be the right level of abstraction. That we could actually get very lost in the details and waste a lot of time. So some examples where we can see where there's no need to look under the hood or make our explanations be in reference to something lower level. We can think of, with this equation here, because we have statistical mechanics and things like that, we can actually just speak in terms of these higher level variables like volume and pressure and temperature. We don't need to be keeping track of what a specific particle is doing where and how it's going to specifically bump into these others. We can abstract away from those details because there's emergence, and there are these emergent properties that pressure is not found in a specific particle, nor is temperature. This is a bulk property that is only true of that system at a higher level of analysis. Another example would be with Zipf's law, where here's word frequency. Although the generating process that would give rise to the words that people speak and things like that depend on a lot of things. Depends on your brain. Maybe to understand the frequency of different words, we should do brain science, or we could go further. We need to do neurobiology or particle physics and maybe quantum phenomena. That's not the place you necessarily look for your explanations. Because we can abstract away from these details, we don't need to look under the hood because of emergence. So with neural networks, we got at one end we've got representations, and at the other end we have neurons. And it seems that there are many phenomena that we can identify with representations or study with representations that we wouldn't necessarily be able to find conveniently with neurons. So one is sort of starting from the top down and the other from the bottom up. Of course, it's useful that people will try both. Maybe we can build staircases between the two levels of analysis. That could help us study both of them more usefully. For instance, if you're trying to study chemistry, or if you're trying to study biology, sometimes it is useful to look at something at the intersection like biochemistry. Now, it doesn't mean you're always going to be looking at biochemistry, but there can be useful relations between these different areas. There's overlap, so there could be some overlap between mechanistic interpretability and representation engineering and some complementary type of functionality, but you wouldn't just choose one or just assume that the more fundamental, lower-level explanations is the right unit of analysis. So that's much more of a philosophy of science type of point. But basically, you should identify that when we're talking about understanding, what does understanding mean? That's a philosophical question. What makes for a useful explanation? This is not something that's an AI-specific thing, so that's why we have to do some detour into what makes explanations more useful than others, and think, well, what provides useful answers in other sort of areas, and what are the reasonable questions to ask in other areas of science. So. What I'll do then is I'll now turn to representation engineering. Basically, representation engineering decomposes into two areas, which would be trying to do things like if we can read these sort of systems or their minds, so to speak, and if we can control them, those are sort of the goals. And so there's representation reading or probing, and there's representation control or representation steering. Many things we would try and do with reading, like try to extract concepts. We would try to discover knowledge that networks have inside of them, that they've gained through pre-training. And we would also try and monitor what's going on inside of them. With representation control, we might try and do things like edit these models. We might try and remove some of their knowledge. We might try and control them in other ways, like have them behave more harmlessly, for instance. Distinctly, what representation engineering tries to focus on is more actionable ways of doing interpretability. What is knowledge for action? A lot of these sort of why are the networks this way type of questions allow you to point at various phenomena, but it doesn't let you actually do new things with those models. So you'll find a lot of interesting gizmos and functionality internally, but it isn't useful for action. So this attempts to be much more practical of if you're getting a better understanding of the internals, then you should be able to use that for control as well. So an example representation reading baseline is we could instruct the model to pretend that it's dishonest, and then we could instruct it to be honest. We could sort of look at how its responses across different layers are, and then we could try to model the difference and identify from that difference in its activations across many examples. We could get a sense of like what does the sort of honest direction in its representations end up looking like. So here's an example of extracting the concept of truthfulness. What we do is we prompt it with an example, like 1 + 1 = 2, and this is the entire prompt. And then we'll try and look at the embedding of that last token of the amount of truthfulness is, where that space is. Then you'll look at the embedding for that. And then you'll use another example where there's something false, and you'll try and get a sense of the truthfulness difference between those two vectors. And you can collect many of these differences, and then if you do something simple like principal component analysis on top of this, then you can get some idea of a truthfulness direction. You don't need to know whether the examples are true or false. You could have two true examples. There'll still be a relevant difference between them, and it can end up working. So it can work in an unsupervised way compared to supervised probes, but that's a sort of a technical aside. So there's things like concepts like power, truth, utility, money, probability. There are also functions like lying or power seeking that you could also extract. And when we're trying to extract functions, we'll do things a bit differently. We'll instead compute like relative differences between each token position. And then try to, with those differences, extract out a direction. But we'll just basically look at applications, and I'll take questions. So for some applications of representation engineering, one would be making the models more honest. So honest would mean truthfully reporting its beliefs. Honest is not the same thing as truthful. So honesty is, even if it's wrong, it's still saying what it thinks the answer is. Meanwhile, truthful, you just need to look at, was its output correct? But when you're going after honesty, you need to have a sense of what's it actually thinking the answer is internally. So you need it to be defined more internally. And we can see that we can basically build like detectors for whether it's being honest or not. We can see for some examples that it is behaving or is having more dishonest thoughts, and we can use that for detection as well. So it sort of knows, you can use this to sort of get a sense of knowing that it's outputting some incorrect information. So it's not just being fooled, it seems to have that representation. You can control lying, for instance, by adding this type of honesty vector to it to steer it to output its actual beliefs. So whereas it would initially lie, then if you add some honesty representation in its intermediate layer, then you can bend it to be more honest. Similarly, this is also seems to be useful for reducing hallucinations as well. There are other things you can do with it, like keep track of, what's its internal concept of how moral this sort of action is, or how related to power this sort of action is. And you could decide to increase the immorality. You can have the morality vector take the negative of that, add it to its representations, then it will output things that it would think are more immoral or more relevant for gaining power. I'll skip past that. There's other concepts you can find inside of networks. For instance, you can see that in later layers you can actually see they're representing different emotions in the middle of conversation. You're not prompting it to do so, but inside it's sort of keeping track of, oh, this person would probably be responding in this sort of way. And then you can use that to also change the sort of types of responses that it would have too, of, well, now it'll behave in a more happy way or in a more fearful type of way. And quickly going through this, we can also use this for jailbreaking. So jailbreaking might happen because it perceives the harmful instructions as safe, or because it knowingly follows the instructions due to other pressuring factors. And we can extract the concept of harm through some data set of, and what we find is that LLMs can still believe that a query is harmful, but still opt to do so when they are being jailbroken. So it's not as though they're always thinking that, oh, because of that random adversarial suffix at the end, those random strings, I think that this is okay. That still pressures them to output the thing, even though it would know that it's incorrect. So GCG is that adversarial attack from the previous presentation. And if we add a harmlessness direction, then that can make it be more resilient to some of these jailbreaking attacks. There are other things you can do with it, like edit facts. You can make it forget, what the concept of a dog is, for instance. So you can get vectors like that. You can make it, oh, woof, domestic cows, maybe they go woof because it had forgotten. So there's a lot of things you can do with this. You could, there's some promising results of using this for identifying memorization or making it output more memorized text or less memorized text. That would probably be a good project because we sort of stopped it. We had to write up the paper, and so we didn't get to explore that very much. But so there's a lot you can do when you're trying to manipulate them at the representation level. If you can get directions and say this direction is doing that, you can say things about the models like, oh, they're knowingly outputting incorrect things. They are complying with the jailbreak request, even though they know what they're outputting is harmful. You can say things about the internals and bend them to behave in better ways as well. So I think that's what we should want from our transparency and interpretability techniques, is an ability to provide, an account of what's going on, and then also how to improve the situation. So wow, okay, so we basically got through three fairly distinct lectures in this of all these high-level risk sources, and then technical lines of research, and then specifically zooming into representation engineering. I think primarily getting research opportunities is a fairly robustly useful thing to do. I think often finding subtopics that people who don't even brand themselves as AI safety researchers, they still might be interested in robustness or data poisoning or interpretability. So I would try and find some specific line of research that is safety relevant, and whichever most talented PI you can find to advise you in that process. And then I would try and work on a variety of projects. If you go down the research engineering route or in the research scientist route, it's still, or PhD route, it still is useful even then. Getting a PhD I think that would depend on like your timelines of whether that's the right idea or not. Do you think that we have advanced AI in a few years? Do you think we have advanced AI in several decades? I think a lot might turn on that specific question for people. But there are many lines of research that people can pursue without a substantial amount of compute in academe. Like this representation engineering stuff, for instance, doesn't require that much compute. So there are tractable subproblems where people can make a difference. So the question is, could representation engineering be used for something like model compression or making it unlearn things? And potentially unlearn so much that it has some narrow understanding of a specific area, but not other areas. So later, when we speak about unlearning, we'll see an application of representation engineering to unlearning. But it's being used to excise a small amount of information, which is basically like just remove expert level virology, but keep everything else, as opposed to only know about one specific subject. So I haven't seen it applied to that, but it can be used for unlearning, yes. So there's a question about a line of research called developmental interpretability. For simplicity, maybe I'll punt in that I haven't seen any papers that have gone through like peer review yet on that, since it's so nascent. So I'll withhold judgment on that area. So there's a question of, can we trace back to the input distribution examples that caused a model to learn some specific concept? And the main line of research there would be like influence functions. And that seems like a useful monitoring tool. I don't know if that helps us understand the inner workings of the models as much. That helps us sort of seem to understand their behavior. So I think that helps improve model understanding and maybe fits into monitoring more broadly. But in terms of understanding internals and inner workings, maybe not as much. So I might just not call that interpretive. I don't know if I'd call influence functions and put it under interpretability, but just another tool in the monitoring toolbox. So the question is, can REPI or representation engineering be useful for understanding the reasoning of large language models? I haven't seen anybody connect the two. I think their reasoning abilities are fairly recent. Like only the very largest models are able to do okay at sort of some of the more classic reasoning tasks, ones that are more complicated and have multiple steps involved. So I think probably I think just a product of it being newer and also there being very few models that have those capabilities, I think it's been understudied. Yeah, so for causality, for instance, you can establish causality or some desired properties through representation engineering. You could manipulate one of the vectors, for instance. You could try and remove the concept. You could try to place in a different concept and see if you still get the functionality. So you could do various things to manipulate the model so as to try to establish some causal connection of what heavy lifting is this representation doing, how necessary or sufficient is it. Okay, so the question is about how do safety and capabilities trade off? So to a first approximation, there's sort of general capabilities that explain most of the behavior of models. So it gets better when an LLM gets better at philosophy and gets better at mathematics and gets better at history, it also gets better at programming because you have a larger model size and it's pre-trained on more and it's using some representations from some areas to help with the other. So I find it helpful to think that there's some sort of general intelligence factor in some models, and then like where does safety fit into that? Is it the case that we can just let its general intelligence continue to increase and then safety is taken care of? And by default, in many contexts, there is a positive correlation between safety, various safety metrics, and capabilities. But that's various safety metrics measuring a specific thing. So Basically, the relation overall is quite complicated. I said by default, so I'm having like lots of hedges. So I'll say more just to give a sense of how complicated the picture is. If you have an increase in intelligence, this can be a double-edged sword. This can help make it more reliable, less likely to have accidents. But this can also make it potentially more hazardous. Now it knows how to cause harm. Now it can make bioweapons. Now it can be repurposed in malicious ways, et cetera. So we can see that intelligence is in some ways a double-edged sword. Safety, I think, generally should try to find areas for it to be useful in the long run. It should try and find sub-areas that are more independent of this general factor of intelligence. So that we don't just have an improvement in general intelligence and then the problem is automatically fixed. So for instance, adversarial robustness is not something that is automatically substantially improved as you scale up the models. You need to specifically try and put adversarial robustness into the models through creating better adversarial training regimes. Likewise, Trojan detection. Can we detect whether there's data poisoning going on? That's not something that is improved as the models, as we change GPT-5, then we're suddenly able to tell whether there's data poisoning. So that's a fairly independent question. So I think interpretability and some of these robustness and AI security type of issues are more independent of and not just straightforward consequences of improvements and capabilities. Likewise, some of these systemic safety applications require specific engineering that are not immediately provided by few-shot prompting a smarter model. So I generally think you want to find research avenues where it isn't basically correlated, strongly correlated with general capabilities, because it will probably be irrelevant when the model scales up in other 2 orders of magnitude, the research. You want to find things that are independent of it, outside of that general factor. What are ways of improving the systems? And that looks like things like adversarial robustness, their interpretability, data poisoning, and various applications for safety. So, so anyway, there's a complicated relation, but there are some sub-problems that are useful to work on and can stand the test of time and aren't just wiped away by larger upstream improvements by the model. Well, I mean, we use it on sort of the largest, or the question is how scalable is representation engineering? We'll have to see, of course, as the models continue to scale, but they're doing well on the existing models, so they can obviously handle multi-billion parameter models. So if they're more complicated concepts, I mean, a slide I skipped over was like a notion of risk, and we can see that its representations of uncertainty or of probability and of utility and things like that can end up being used to model more complicated concepts like risk. But yeah, I think for a lot of these, we'll basically have to see what interesting things we can find from these models. But so the question is, what are improvements, or what are changes to make from unsolved problems in ML safety since it was 2 years ago? So it had, there are some things in it that basically we're putting it before there are any papers really written on it. Like honesty is sort of a thing that we look into now, and like lie detection is the thing we look into now, and that was in the paper. Likewise, unlearning and model editing and things like that was also in the paper before there were many papers on it. There's also the systemic safety stuff is pretty related to this defensive accelerationism or Vitalik-Buterin type of concept of let's try and make the world like generally safer. So I think it's standing the test of time well. I think probably, I guess representation engineering would probably be something I would add to it. And more transparency and interpretability stuff. There's not much a focus on transparency or interpretability on unsolved problems because at the time I think it was basically, you basically were stuck with saliency maps and feature visualizations, which I just didn't think were not going to stand the test of time, and they weren't, so hence they weren't included. But in terms of new topics, then yeah, I probably would just add the more recent promising stuff on interpretability.